Hi everyone, I am Anil, and in this video I shall briefly go through designing an LNA for a given set of specifications. So this set of specification is taken from the RFIC website E6320 2024. Right, so this is the website, and this is the project which I shall demonstrate here. This is a differential cascaded common source low noise amplifier for this frequency band, that is 5.17 to 5.32 gigahertz. That is the frequency of 5G WLAN 802.11a, and you are supposed to use this topology, that is differential cascaded common source low noise amplifier, and the technology that is supposed to be used is IBM 131 nanometer process that has a supply voltage of 1.2 volt, minimum lengths and widths as follows, and the specifications are as such. The range of frequency of operation is 5.17 to 5.32 gigahertz, and the center is this. So directly using this, you can get the corresponding Q of the network that is required. Note that this Q needs to be lesser than the values of the Q values of the inductor. If the Q is more, then you will have to externally compensate for the Q of the inductors. That can be done using negative R. However, nonlinearity might be an issue. That we will not look at that for this project. It is not necessary. And the differential input impedance, as for any RF system, needs to be 100 ohm. So that means the single-ended looking in impedance needs to be 50 ohm. In RF terms, this input impedance specification is written as S11. S11 basically refers to input matching. It needs to be sub minus 10 dB. It also represents the insertion loss if you neglect the sign, and that needs to be less than 10 dB throughout this bandwidth. And to make this single-ended to differential conversion, we are going to use an ideal balance. We'll learn on how that is done. And the second set of specifications is the voltage gain. That needs to be greater than 20 dB. Note that this is the voltage gain, which means you need to do the differential output by the differential input, and only that. We are not worried about matching at the output. Again, there is no spec on S21 or S22 here. Just a reminder. And another interesting fact is that this LNA is used to drive a mixer with 100 femtofarad differential or 200 femtofarad single-ended load. So this is the load of the mixer as well as any process tuning. So this can be updated once we do the mixer, which I will show in the next video. And the gain flatness of the band should be sub 2 dB. So there is the only way we can control this is using the Q of the network. If you do an extremely high Q network, which is probably not possible due to the Qs of the inductor. However, if you can somehow manage to do extremely high Q, this spec might get violated. So, however, it is probably unlikely that in this case it will get violated because of the limitation on Q of the inductors of 20 at 5 giga. And the noise figure needs to be sub 3 dB. And the IIP3, that's a measure of nonlinearity. And this IIP3 is even interesting measure. So you inject two tones at the input, and two tones that are very close to each other, separated by say 1 megahertz or something, and then you measure the third harmonic amplitude at the output, and you find out if that is less than a certain value, and that gives the spec on IIP3. And this is a very subjective spec on minimizing power dissipation. This is all these three cannot be easily controlled, though one way of controlling IIP3 is to increase the current in the network, but that will automatically result in a trade-off with the minimum path. Anyway, we'll look at how all of this is done. So moving on, I will refer to this paper, that is a noise reduction and linearity improvement technique for a differential cascade, to just demonstrate how the structure would look like for a single-ended LNA. So this is a simple inductively degenerated cascade common source LNA, which is what we will build. So this is the input, So this Vin is a voltage source and with the RS of 50 ohm, and this drives this low noise amplifier, which is having this input circuitry, LG, CGS, and LS. The purpose of this circuitry is to provide matching at this input, and in simple terms, this the resonant frequency of this network given by 1 by 2 pi square root Lg plus Ls times this CGS should be the center frequency of our interest, and the real part of the impedance that is seen here, that is omega t Ls. Omega t of this transistor can be given by Gm over CGS. That should be 50 ohm for input matching. So that is the constraint here. And the cascode is used here to provide isolation between this output port and the input port. Otherwise, due to this CGD coupling, there can be a flow of signal from input to output via this capacitance at RF. So we don't want that. That is why this cascode has been used. And at the output, again, we'll design a resonator tank at the output so that we get the output resonance also at the same center frequency. And we need to ensure that the Q of this resonant network and the Q of this resonant network is the same, so that the circuit behaves optimally for us. So now we'll delve into the schematic which I have implemented in Cadence. So this is the schematic of the differential common source amplifier. This is there are two parts to this. The first part is just the schematic. We'll test the whole circuit in something called as a test bench. So there are two blocks. One is the schematic, other one is the test bench. Now we'll look at the schematic. So in the schematic, as I just showed, this is the differential common source LNA design for the single ended. The same thing has been replicated on the right side and made fully differential. So positive input will give negative output because the gain is from here to here is negative, and likewise here. And this is a simple current mirror to bias this input pair. Note that you should always use negative feedback based current source biasing. That is advisable over simple voltage source biasing due to PVT variations. And as you can see, I have used these inductors. And to use any element in the library, you just press I, go to this library analog lib, and select the element you want. Right. So for NMOS, I type NMOS and pick NMOS 4. And in the NMOS 4, I need to specify the model name. For 130 nanometer CMOS by IBM, it is N sub 18 sub mm, as I have typed it out here. For example, in TSMC 180 nanometer, it is CMOS N or something similar. So just type it, and for the first iteration of the network, please use the hand calculated values of the lengths and widths. Typically, the length is at minimum length. You need not worry about these parameters. So once that is done, you can use, this is the NMOS. Ind Q we shall use for inductors. We need to give a quality factor of 20 here. That's what the maximum spec is. And this frequency needs to be given at 5.245 giga, as has been mentioned, and we input the values. Note that I can keep these as variable as well. I have kept it as variable so that uh, I will vary these variables in the ADE window. And then show how it works. So this is for an inductor, RES is for a resistor, and CAP is for a capacitor, right? And to write any label, you can press the word L, key L, and you will get an option to create wire name. Like for example, I can name something as VDD and paste it here. And to undo any operation, press U. And to instantiate something like a pin, press P, and you can choose the type of pin you want. And to create any wire, press W and just draw a wire. All these shortcuts are pretty useful. And as I explained before, this is just for the resonance. This is to bias the transistor. This is to cap couple at the output. This is the load of the mixer. This is to cap couple at the input. So this is the schematic. It has been iterated over several times, and these are the final parameter values are in the ADEL window, which I will go through later. And so once you have designed this schematic and you have put the respective pins, so pins are where the signal comes into the network. It could be input output. If you don't need to access internal nodes, you can put it as, you can just neglect it for the time being. And you go to create cell view. From cell view, and then you pick this. Then you can create a symbol like this. You can create, right? So I have already created the symbol, so I'll just go through and show how the symbol looks. So this is the symbol of the common source LNA which I have created. So Cadence by default allows you to manipulate the symbol in however way you want, and it is usually good practice to keep the inputs on the left, outputs on the right, ground rails at the bottom, supply at the top. That is the convention we follow in most schematics. And once this is done and the schematic design is also done, we move on to the test bench. This is where we will test the circuit. So in the test setup, I have once your symbol is ready, press I and go to the library where you are operating and press take the name of the library and find the name of the symbol which you have created. This is, for example, something else, and this is from something else. So you once you create the symbol, you can just keep it here and then do the same thing. So here I have used a bias of 1.2 volt, and this bias V bias is generated using this current mirror as I showed previously, and this ground goes to ground. And this balun can be obtained from the RF library. To type balun, you can either choose balun com or ideal balun. Balun is the best one. And you set single input impedance and balanced output impedance to 50. Do not give any insertion loss. And then you do this. And then you set up the port. This port has been used to measure both AC and S parameters. So I'll just briefly go through setting up of the port. So this port has an input resistance of 50 ohm that is standardized by RF, and the source type is set to sine. The first frequency is named RF1 with a frequency of FRF. I'll define all these in my ADEL window. And the second frequency is named RF2 and it's given at a frequency of 1 megahertz off with the same amplitude PRF. And I've set display small signal to be true. This is for AC simulation. And note that I've given the AC magnitude of 1 volt. And this is named port 0. So I have named the input port as port 0 and output port as port 1. And this bias current is IB. So all these are set up in the ADEL window. Suppose you forget to initialize one parameter, say this M is the multiplier, I forget it. So the advantage with this ADL window is, in case you forget something, that is described, it'll automatically flag an error. And this is not coming because I'm not check saved. So you have to check save all the schematics. So once you have check saved and press play, since I forgot to mention the multiplier M, the error came, as you can see. And I'll specify the multiplier as 1, which was the thing before. And the remaining parameters have been fixed after iteration. And just before that, you have to set up the model file. Just ensure that your whatever model file you are using has been mentioned here with its right path. And that completes the setup of this. And this is the setup of the design variables. The analysis is pretty simple. You just go here, right click and then pick the DC. Any circuit needs to be first checked with its DC operating point, whether you get the required details or not, etc. etc. So you do this DC operating point. Just click on save operating point. Okay. Similarly for AC, you go to AC and give your sweep range 5.1 to 5.4 and 2K points, and go to SP also and give the ports in the format input and output, and you give the same frequency range as AC, and then you give the number of steps as well. and then select this do noise and give output port as port 1 and input port as port 0. And then you go to HB, and then here in HB you select, you keep run transient decide automatically, tones as names, and pick the first tone, that is RF1 5.245 giga, that has been set here. And select the sweep option and press select. It's not a frequency variable, it is a power variable, PRF. And typically you can sweep from pretty low values to pretty high values, that is -60 to -20. It is in dBm, by the way. And I've given 20 points of sweeping. So once this is set up, you just have to press play, and Cadence will take care of the rest. So as you can see, it is sweeping. In case any issue pops up, such as error, you can go to this log file and figure out what the error is. And once the simulation is done, go to results. The first thing you have to check is the DC operating point. So go to DC operating point, click on the MOSFET, you will get its operating point, right? So once this is, you can see what region. So region is a good way of finding out where your MOSFET is operating. 0 stands for cutoff, 1 stands for triode, 2 stands for saturation, 3 stands for subthreshold. You need to operate in region 2 as you would want here. And you can use this VDSAT to get an estimate of the VDSAT. You can use either VDSAT or VGT, both are okay. You can check the threshold voltage of this device, which is VTH, and you can check how much current is flowing, and you can also check whatever GM value you are getting here, and you can also figure out the FT of the transistor. It is designed to work at any frequency in the model file. This is not true in reality if you use a PDK transistor. And you can get estimates of CGD, CGS, CDD, CGG. So all the CGG, CG, CDD are all the one terminal equivalent capacitances looking at the gate drain respectively, gate comma drain respectively. And you can also look at CSG, CGS. They are coming out negative because that is how the simulator has defined it. You need not worry how this works. To get the exact measure of resonance, just ensure that your ZM1, as I shall show later what ZM1 is, peaks at the required frequency. Okay, so once that is done, I just went to ADL, pressed results, and direct plot main form, and you get this window. The first thing we look at is AC. So AC we look at in dB20 how much there is voltage gain, that is at the output. Since I gave 1 volt input amplitude, I can go directly and check how much AC gain I'm getting. So this is a plot of AC gain. This is something old. So this is a plot of AC gain, and as you can see, we are getting way larger than what we expected. It goes from 35.5 to 36.5, flatness of say 1 dB. That meets our flatness spec, and the spec of 20 dB, as you can see, is met without breaking a spec. And to get any point on this curve as a marker, press M. You'll get this point. And to measure any distance, press D. You can measure a distance between 2 points. And you can type any label on the graph, press L. If L is not working, press insert, create graph label, and type whatever you would want. Say here voltage gain. Right. So with this, the AC gain specification has been met. Now we move on to checking the next specification. That is the S parameter specification. So in S parameters, you have several ones. You can check S11. S11 is a measure of input matching. So as you can see, the network is pretty well matched, as you would expect. It's sub -13 dB throughout all frequencies. And this is S11. We'll check S21 as well. S21 is also pretty close to 20 dB, as we would expect. Though the spec is not an S21, we are looking at the spec of S21 as well here. S21 represents the power gain from input to output. The spec is on voltage gain, which is AC. We are not worried about power gain. However, I'm just showing that you can also check for S21. And the last thing we need to check is noise figure. To measure noise figure, press NF, go to dB10 and press plot. As you can see, the noise figure is sub 2 dB, which meets our specification. Our spec was 3 dB, however. Uh, and you can check this plot of input impedance, which is Zm. So to check Zm, you can check at the input as well as output. Zm1 is the input impedance, Zm2 is the output impedance. You can check the real part. It is around 50 ohm, which gives good matching. And similarly, you can check the imaginary part if your resonance is met correctly. And several other parameters are there, which I will not delve into in this video. Uh, you can use ZP or YP as well. They will give you Z parameters and Y parameters. Now we shall go to HB. HB stands for harmonic balance. It is used to measure the IIP3, etc. So in setup, you go and select port. Then you select this option of variable switch. Then it just defaults to this. In the third harmonic, you have to select RF2, 2 RF2 minus RF1. That is the coefficient here. So we have this convention. Omega 1 is my center, that is 5.245, and omega 2 is 5.246. So my third harmonic is at 2 omega 2 minus omega 1, which is 5.247. And my omega, the first harmonic is at omega 2, that is 5.246. So you select this and select the output port on schematic. So once you select that, this will plot the IIP3, and the IIP3 obtained is -7 something, which meets our specification. So with this, uh, as I showed earlier, this extracts from a very low value of power input, that is in dBm. -60 dBm is like -90 dB, which is extremely low. So it's roughly linear, and as you can see, the circuit starts behaving non-linearly at around this point, and then the linearity is obtained at this point, which is -7 uh, dBm. This is also extrapolated. Maybe you can sweep slightly more. However, I won't show that here. And so that completes the design of this low noise amplifier. So if you have any questions, you can post them in the comments or you can email me. Thank you.